An octopus is sitting quietly at the bottom of a tank. Nothing is threatening it. The water is still, the temperature is fine, there is no predator nearby. And then slowly and deliberately it reaches one of its arms toward its own beak and begins to eat it. Not because it's starving. Not because the arm is injured or infected. The arm is perfectly healthy tissue. The octopus is simply eating it, calmly, as if it were any other piece of food. Aquarium keepers and marine biologists have documented this behavior in multiple species under captive conditions. It even has a clinical name, autophagy, and it raises a question that is surprisingly hard to answer. If evolution is ruthlessly efficient, if it weeds out anything that reduces an animal's chances of survival, why does it keep producing an animal that destroys its own healthy tissue? What kind of body is built to eat itself? Stay with me. Because the answer isn't a flaw in the octopus, it's a window into one of the most genuinely unusual body plans that evolution has ever produced, and what happens when that body plan reaches its limits. To understand why an octopus sometimes eats its own arm, you first have to understand something about how an octopus is built, something that sounds almost impossible the first time you hear it, and that changes the question entirely once you do. Your brain controls your body. Every movement you make, every sensation you feel, every decision about where your hand goes next, it runs through a single central command system. Your arm does not have opinions about where it wants to go. It goes where the brain sends it. An octopus has approximately 500 million neurons. That is a substantial number, more than many animals considered far more complex, but 2/3 of those neurons are not in the brain at all. They are distributed through the 8 arms, roughly 50 million per arm. Each arm has its own local nervous system. It can taste what it touches, respond to stimuli, and execute complex movements completely independently of the brain. Researchers have shown that a severed octopus arm, fully detached from the body, will continue responding to touch and attempting to pass food toward where the mouth used to be for up to an hour after separation. The brain sends broad instructions: explore that area, find something to eat, get away from that, and the arm works out the details entirely on its own. The specific route, the individual sucker grips, the micro-adjustments in real time. The brain often has only a rough sense of what each arm is doing at any given moment. What this means is that an octopus is not one mind controlling 8 limbs. It is closer to 9 semi-independent systems, 1 central, 8 peripheral, that usually cooperate and occasionally, under the right conditions, stop cooperating entirely. Now, the arm eating. And here is where the distributed nervous system stops being a marvel and starts being a liability. When an octopus is under severe, prolonged stress, poor water quality, inadequate oxygen, an untreated infection, extended captivity without enough environmental complexity to keep those 9 semi-independent systems occupied, the coordination between those systems begins to break down. The arms, which already operate semi-independently, start to behave in ways the central brain can no longer regulate. They move erratically. They don't respond to the brain's broad signals the way they normally would. In severe cases, 1 or more arms may begin approaching the beak, and the octopus may begin to bite. The leading hypothesis among researchers who study this is that the breakdown in neural coordination causes the brain to effectively lose track of the arm as part of itself. The signals that normally say "this is mine," "this is me," "this belongs to the system," those signals degrade or disappear, and an octopus that does not recognize something as part of itself will treat it the same way it treats anything else it encounters that it cannot identify as a potential food source. It is not a choice. It is not self-destructive behavior in any intentional sense. It is the result of a body organized around distributed coordination reaching a point where that coordination collapses, and the parts of the body that were always somewhat independent finishing that journey the rest of the way. Now, the part that should stop you completely, because it reframes everything that came before it. The arm grows back. Within weeks, 5 to 8 in most documented cases, depending on species and the individual animal's condition, a new arm has grown to replace the one that was lost or consumed. Not a scar, not a simplified stub, a full functional, anatomically complete replacement arm, with its own suckers, its own musculature, and its own local nervous system. The regrowth process begins almost immediately after the arm is lost. The wound closes, a regenerative mass of cells forms at the site, and the new arm begins to develop from the tip outward, suckers first, then the internal musculature, then the neural connections that will eventually link the new arm back into the distributed network. The arm that was eaten was not in any permanent biological sense a catastrophic loss. It was closer to a resource the body consumed and then replaced. The system that ate the arm and the system that rebuilt it are the same system, and it appears to have been designed through millions of years of evolution to be able to do both. Here is what the arm eating and the regrowth together force you to reconsider, not about octopuses specifically, but about what a body actually is, and what the word self is even pointing at. We operate with an intuition that the body is a fixed, unified thing, a closed system with a clear boundary between what is self and what is not. Damage is damage. Lost tissue is lost. The job of the body is to maintain the boundary and protect what is inside it. An octopus does not appear to operate under this assumption. Its body is modular in a way that ours simply is not. The boundary between self and not self is under enough stress, genuinely negotiable, and the cost of losing one of 8 semi-autonomous arms that were already operating with a great deal of independence, appears to be something the system can absorb and recover from. What this means is that the question we started with, why would evolution produce an animal that eats itself, may have the wrong frame. Evolution didn't produce an animal that eats itself. It produced an animal with such a radically different architecture of self that the occasional loss and replacement of a limb barely registers as unusual. It is one of the things a body like this does. Go back to that octopus from the beginning, sitting quietly at the bottom of the tank, calmly eating its own arm while the water sits still around it, and nothing in its expression suggests anything unusual is happening. It isn't broken. What you are looking at is a body organized around principles so different from your own that words like self and loss and damage don't quite map onto it cleanly. It is operating by its own logic, a logic that has worked in various forms for hundreds of millions of years. 9 semi-independent nervous systems, arms that think for themselves, a body that occasionally eats a piece of itself and then rebuilds it from scratch, and underneath all of it, something looking back at you through the glass that we don't have a good word for yet. Look a little closer next time you're near one. Of all the minds sharing this planet with us, the octopus might be the one we understand least, and it might be the most interesting one to start with. If this changed how you see an octopus, if the one in the tank at the aquarium looks different to you now than it did before, subscribe. We keep pulling apart the hidden systems behind the wild. I'm still out here watching, and the more I watch, the more I'm convinced that the strangest minds on this planet aren't the ones we usually think of. I'll see you in the next one.